Sweet. We are
Coming to you
live,
live,
every.
live, live.
Awesome. All righty. Well, good day wherever you are joining us from. I'm Melissa Riley, your co-host today, joined by a new guest from Hazelcast, Director of Education Services, Hendy Appleton. How you doing, Hendy?
It is a great morning over here in Oregon.
How's the weather in Oregon?
It's raining, but that's the Pacific Northwest for you. We get 9 months of rain and then 3 months of no rain. So I'm enjoying the last of it before I have to start watering my garden.
Oh no. Yes. I need that water too for my tomatoes. All
Oh,
Well, I'm looking forward to learning more about CP subsystems, but before we dive into the content, a quick heads up to everybody joining us. This session will be recorded and you'll have access to the recording for later viewing. And also feel free to add any questions you have in the chat, and Hendy will address them either on the spot or during our Q&A. And I guess without further ado, Hendy, I will hand it over to you.
all right. Let's do this thing. I just want to start with going through a few things, and hopefully this doesn't decide to start auto advancing it. I wanted to just kind of level set on what CP is versus AP. So if this is familiar to a lot of you, yeah, it is going to auto advance. I don't like that. Um, so we're just going to do it the ugly way inside PowerPoint. Sorry, guys. Um, so what happens when you use material that you have actually used for creating training, that education services, what can you do? So if you're not familiar with the CAP theorem, this has to do with how a distributed system handles data. You have a choice. It's a best 2 out of 3 type of situation. The CAP stands for consistency, availability, and partition tolerance. So consistency, it means that the data is always that a client gets, that a application gets from a distributed system is always the most current, most up-to-date data. And if we can't deliver the most up-to-date data, we don't deliver anything. Availability means we will always deliver something. Whether we're not going to make any guarantees, 100% guarantees that it is the most up-to-date data, but it is your application doesn't come to a screeching halt because you're not getting any response at all. And then partition tolerance, partitioning, if you're dealing with the distributed system, you have multiple individual systems that are part of that cluster. What happens when those individual systems can't talk to one another? Are we still going to deliver data or are we going to do nothing? So the system needs to continue to operate despite delays in communication between those cluster members or the loss of individual data between those cluster members. So that's the CAP theorem. And the summary of the CAP theorem is you get 2 out of 3. You can either have consistency and partitioning tolerance, you can either have availability and partition tolerance, or you can have consistency and availability, but then the system completely falls apart if there's a partition in your system. The reason this is important is because Hazelcast as a system is predominantly an AP system. I'm going to do this a little bit differently. So I'm going to see if I can get control over this. Okay, so if you have this is a typical Hazelcast cluster. Under normal operations, I'm going to be clicking back and forth here, guys. Because I want to show the slide builds. So under normal operations, you've got three cluster members, 2 client applications that are communicating with your Hazelcast cluster. Under normal operations, everything is fine. The different clients are going to be talking to one another. Stop. Yeah, this is just not going to work. I apologize. I've got pre-programmed advances here. So the big part of and I don't know how to freeze that, which is really the annoying part of things. I know how we do this. Ha. Get rid of all of that. There we go. Bingo. Yay. Okay. So cluster under normal operations, everything is fine. Both clients are communicating with the cluster. And if client A tries to write something, the Hazelcast normals threading model is going to make sure that when client A writes the data, client B can't access that data until client A's write is complete. And it's just because of the way that we do threading with our partitions. So under normal operations, we're going to be able to provide you with availability and consistency just inherently to the design of our system. Where we run into issues is when there is a partition in the cluster. So now we've got a situation where client A is talking to part of the cluster, client B is talking to a different part of the cluster. What happens? Availability says that both client A and client B are going to continue to operate. They're going to continue to write to data fields. So they're going to be writing. We're going to keep operating during a network failure. Apps are going to continue to write data. So now what happens? So client A updates a map and says that key 3 is a value of C. Client B does the same update, but they update it so that that key has a value of Z, which is correct. Do we allow that operation to even continue? Do we allow these systems to continue to write when we're in a partitioned state? Now, Hazelcast, as a predominantly AP available system, Hazelcast will allow this to happen. And then when the cluster gets healed, we have split brain protections, and there's all sorts of algorithms that we can run that will determine which is the more correct data. But that's not what we're talking about here. What we're talking about here is we don't want this situation to happen. If we have to guarantee that the data that we provide is 100% correct all the time, we can't allow this condition to exist. We can't allow these two clients to continue to operate under a CP consistency, or concurrent consistency systems, consistency first. So, when we're in this partition situation, we have to ask that question. We can't have both consistency and availability. What are we going to do? Hazelcast by default, using our map data structure, the IMAP, will default to availability. But if you need consistency, that's where the whole CP subsystem comes into play. If you absolutely have to ensure that you are not getting into the situation where you have clients that are accessing and potentially writing and reading inconsistent data under these partition conditions, that's why you need the CP subsystem. So that's where that comes into this equation. The CP subsystem runs alongside the normal Hazelcast AP system. So the Hazelcast that you have been using all along still exists. Nothing's changed with that. And so all the stuff that you know about IMAP and all the stuff you know about split brain, that still applies. What we've added is this CP subsystem that provides consistency for the data structures that require it. So, for example, Java concurrency primitives, right? Those are all now going to run under the CP subsystem to ensure that we have absolute atomic operations under all conditions, not just when the system is running like it's supposed to. So, for those of you who are familiar with the Jepsen test, right? That is the authoritative test for consistency. We've always had these the Java concurrency primitives, and again, under non-partition conditions, everything was fine. Our system was designed properly. And the way that we implemented those concurrency primitives was also okay under most conditions, but we failed Jepsen tests. We just failed. So that was why the CP subsystem was created. And it's been around, the CP subsystem is not a new thing to Hazelcast. We've had it around for almost 5 years. In 5.4, we added a whole bunch of modifications and performance improvements. And the big thing that we added was the CP map data structure. So now you have not just the Java concurrency primitives, but you have an entire map key value store that is guaranteed for consistency. which is that's a IMAP is the most IMAP in our AP system is the most commonly used data structure by far. You now have the ability to use that same data structure, that same familiar key value store, but guarantee consistency for data, which is a lot easier to manage than trying to manage potentially hundreds of atomic references, for example. So how do we guarantee consistency? We use the RAFT consensus algorithm. Again, that RAFT is the industry standard for guaranteeing consistency within a distributed system. We've implemented it, we use it, it works great, and we now pass all the Jepsen tests. If you want to, you can go to the Jepsen GitHub repo and you'll see Hazelcast under there. We also have our, under the Hazelcast GitHub repo, there's the Jepsen test. So it's duplicated in both places. So don't take our word for it. It's there. You can go see it for yourself. So again, the difference here is that if you've got using IMAP, under partition conditions, IMAP will return data. Under partition conditions, CPMAP will only return data if we can guarantee consistency. I'm going to show you how that works in the next couple of slides. So these slides are extracted, by the way, from the Strong Data Consistency course. That course is available on the training website, training.hazelcast.com. I encourage you to take it if you have more questions or want to explore any of these concepts in more depth. You will hear my lovely voice because I narrated that training too. So I'm just going to show briefly how we guarantee consistency. So this is under normal operations. When you're working with the CP subsystem, you are working with a group of cluster members that are going to be holding that data. We'll talk about configuration later, but basically that group is always an odd number under normal operations. The reason is that when you partition something that's an odd number, you're always going to have a majority and a minority. Majority rules. Okay, if you're familiar with that term, majority rules. So under partition conditions, the majority can continue to operate, the minority will cease to provide responses because we can't guarantee consistency among that minority. We can only guarantee consistency with the majority. How do we guarantee that consistency? Back to the slide here. So this is how RAFT works. The client will write to the cluster. So here's my data update. Within this group, there is a designated group leader. The group leader will add that write to the internal log saying, okay, we've got data that we have to update. It's then going to send that update to all the other group members saying, okay, everybody, here's the newest data. Don't respond to anybody yet. Let's make sure that we are all consistent and we all agree that this field is now set to 8. When the group members add that to the log, they respond to the leader saying, all right, we're ready, we agree. When all of the group members respond, then the group can commit that data and make that data available for reading. That's in short how RAFT works. So now that data is, so we have to go through those steps. And the first thing anybody should say is, wow, that's slow. And compared to an AP system, RAFT does slow things down, but you're trading a guarantee of consistency for this performance hit when you write data. Now, this is only when you write. When you read, performance is the same. We're still reading data out of memory, just like we do with IMAP. So you are taking a performance hit, but you're trading performance for consistency. And if you are working in any industry where consistency, that data has to 100% be correct under all conditions, it's worth the trade-off. So, okay, moving on. So how do we deal with this when we're partitioned? Right. This is where the CP subsystem comes into the idea of guaranteeing consistency comes into play. So we've partitioned now our group so that we have a majority and a minority. If the majority is available, that part of the group will continue to operate. So in this situation, client A is still going to have access to all the data, is still going to be able to do reads, still going to be able to do writes. Everything is fine because we can still run raft between those two group members. We are still able to guarantee that there is consistent data in that subset of the cluster. What we can't do is with the solo client, because he's got no majority, he's got nobody he can agree with, that part of the CP subsystem will not respond to requests for data, will not respond to any writes. It's just, I can't, I'm a minority member. So that's the difference, excuse me. That's the difference under those partition conditions. We guarantee consistency. If we can't guarantee it, we're not going to respond. Now, I know you're probably wondering, what about CP4 down there? What is he doing? We'll get to that. Remember, groups are always starting with an odd number of systems. Okay, so when we form this group, in this situation, maybe we have 4 cluster members, a group is only going to start with 3 because we have to have that majority. If we started with 4, how would we know which side has the majority? We cannot guarantee consistency across a partition structure that has, when we started with an even number. Now, again, you're okay, well, wait a minute. Now we're under partition. What happens with the CP subsystem if we have client or cluster members 1 and 2? What happens if cluster member 1 dies? Well, then the whole CP subsystem stops responding because we don't have majority anymore. And again, if you're thinking that's bad, that's by design. We cannot guarantee consistency. Also, I will point out that concurrently with this, you still have your Hazelcast AP system. You still have your IMAPs. You still have all those other data structures in there. Those are still working. Everything is responding as normal under normal partitioned operations. It's just specifically the CP subsystem that is doing this and all the data structures in the CP subsystem. So those concurrency primitives and your CP map, because you implemented those so that you can have consistency 100% all the time. Okay. Now, the cluster members do retain their group membership in memory. So if this partition gets healed, cluster member 3 will come back online and say, hey, group, I'm back. The leader of the group will update cluster member 3 and operations go back to normal. I think I just said that. Leader will update returning members. Okay. And again, as I emphasize, this only affects the data stored in the CP subsystem. AP will continue to operate. So that 4th cluster member, let's talk about that guy for a second. Okay. When you set up your CP subsystem, you're going to back up for a second. When you set up a cluster, all of your cluster members should have the same configuration. So if I have a cluster of 4 members, I have choices here. Choice number 1 is to say my CP subsystem will start when I have enough members to form a group. And a group can either be 3, 5, or 7 Hazelcast cluster members. In this case, it's going to be 3. So I can have the CP subsystem start with 3. The CP subsystem itself will start up, form a group, start allowing data writes and reads when 3 of these 4 cluster members first join the cluster. When the 4th member joins the cluster, it's CP subsystem aware, but it's not participating in the CP subsystem. The CP subsystem set itself up and started running before the 4th member joined. I'm actually going to demonstrate this and demonstrate the differences between these two. So why this matters, because it specifically has to do with the resilience of your CP subsystem. So when this starts up, the first 3 subsystems to start will show up in the CP subsystem. If one of your if there's a partition, the group will heal itself. If a cluster member that's in the group fails, and just disappears from the network for whatever reason, if it has persistence configured for CP, what that means is that it's also been writing the CP subsystem contents to disk in the background. When it boots up, it can pull that the knowledge that I'm a member of the group back into memory when it starts back up. When that happens, it can automatically rejoin the group. It's as if it was partitioned away. So we can recover from not just a network partition, but we can recover from a cluster member restart if persistence is enabled. That fourth system, okay, if the restart fails, then there's manual intervention that has to happen. So, or if there is no data, if you don't configure persistence. So cluster member 3 reboots for whatever reason, it comes back up and it doesn't have any knowledge of its group membership. It knows that the CP subsystem exists because that's in its configuration, but group membership is negotiated dynamically. It came back, it has no knowledge of group membership. The other two systems know that it's supposed to be in the group, but he's not reporting in as a group member. Therefore, he can't rejoin the group. Okay, so the key is I have to have group information in memory. If persistence is configured, I can pull that from disk, put it into memory, and it's as if the network was partitioned. I'm going to rejoin my group. If it's not in memory and I rejoin the CP subsystem, I can't automatically rejoin the group. I can manually, if an administrator goes in, removes the failed system, and then adds it back in to be available as a group member. And again, I'm going to show you how to do this. But before you start thinking this is a lot of administration, remember this only is going to happen under these, how often do your cluster members fail? If your cluster members are failing all the time, you have a bigger problem than managing your CP subsystem. If your network is partitioning all the time, you have bigger problems than just managing the CP subsystem. So keep that in mind. These are not everyday occurrences, hopefully. So this is, again, the key is, do I have the data in memory? If I set up my CP subsystem with 3 members, the 3 will join the group. If a group member then fails, it has to be able to pull that data into memory. Otherwise, it requires manual intervention. If I don't configure persistence for whatever reason, I don't have a disk available, I don't have disk space, whatever it is, I can set up my CP subsystem for auto promotion into a group. That's where that 4th member comes in. If I set my CP member count now to 4, the CP subsystem won't start until all 4 members boot up. This is only at startup. That number only matters at startup. But it means now that that 4th system is available to join a group. Before, when the CP subsystem started up, it started with the 3 members. That 4th member came along and it's CP enabled, but it wasn't available to join a group because it wasn't there at startup. Here I'm saying, no, don't start the CP subsystem until all my cluster members are available. Once that happens, that means that all my CP subsystem members are available to join a group. The group is still only going to be 3. But what it means is that we're still going to start the group with 3, but we have these now important numbers here of time to live is 5 minutes. CP auto removal is 5 minutes. By default, that auto removal is 4 hours, by the way. So again, we're giving time for network partitions to heal. In this situation, we're saying, hey, I got an extra guy here sitting here. So if there is a problem, say member 3 fails again, okay, go back to, we still have a majority. So the clients have never been aware that any of this is going on, even in the previous situation, right? We're talking about not a partition now, we're talking about a member failure. in that situation, I still have a majority. The clients are still able to talk to the CP subsystem. This is all managing my resilience and managing everything in the background before something crashes and affects our application. So in this situation now, clients or members 1, 2, and 3 were in the group, and member 4 is now on standby. If member 3 fails, after 5 minutes, the group says, hey, member 3 is gone. We've reached our timeout. Is anybody else available to join the group? And member 4 is available to join the group. Member 4 will join the group, bringing the group count back up to 3. Operations continue normally. And again, this is all happening in the background. Your clients are not going to be, your application is not going to be aware that this is happening. It's not going to affect your performance. This is literally just configuring for resilience, right? Configuring for that extra something goes wrong. If, by the way, in this situation, when group member cluster member 3 comes back online, you will still have to manually tell number 3, you are now available to join a group. You will still have to do manual intervention, but you haven't lost your, your complete group complement. You haven't ruined the rest of your resiliency with that. I say, yeah, returning member requires promotion, and promotion is the term we use for saying you are available to join a group. We'll be using Management Center to do all of these operations. So the CP map data structure, this is what we added in 5.4. As I said before, we've had CP subsystem for a while. In addition to a whole bunch of performance improvements and operational improvements, we added this CP map data structure. So it's a key value store, just like IMAP. If you've used IMAP, it really is for programming purposes, it's the same data structure. It's just being stored in this consistency subsystem because you want to have 100% guarantees of consistency all the time. If I got a screen capture here of the IDE that I use that shows, here's all the operations, and these operations should be familiar to you. It is currently, I think I have this next slide. Yeah, okay. So for 5.4, it only does point operations. So get, set, put. Querying is coming. I believe it's in 5.5. I'd have to check the feature list again, but the ability to query data structures in CP is coming. It's just not there yet. This idea of unsafe mode. This goes back to the concurrency primitives. We've always had those concurrency primitives. You could run them in an AP-only system. It just wasn't providing 100% all the time guarantees of consistency because we weren't using Raft. So under partition conditions, those concurrency primitives without the CP subsystem weren't actually 100% concurrent. That's why we failed the Jepson tests. We call that unsafe mode. If if you use those without CP subsystem, it's unsafe. It's not 100% guaranteed. CP map only works if the CP subsystem is enabled. If you don't turn on CP subsystem, CP map isn't even available as a data structure. And this is important because when you're creating your coding environment, go back up for just a second. We showed you that you have to have 3 cluster members to be able to run the CP subsystem. So that means that if you are a developer and you need to use CP subsystem, you need to set up a development cluster that has 3 members. Now you can do that easily in Docker. We're going to do that in a second. In fact, I think that is what we're going to do right now. No, sorry. I have some best practices for you first. Because CP, the whole idea of writing to the CP subsystem does incur an additional overhead. You want to make it as performant as possible. Use set and delete rather than put and remove for accessing your data if you don't need that old value. And by the way, this is also true for AP. This is not a CP subsystem thing. This is a, why incur an extra round trip of returning data that you're never going to use? All right. So a put returns the old value from that field. If you don't need it from that key, just use set instead. Some capacity planning rules that have to, making sure that you have enough memory for your CP data structures. I will leave that for your additional reading. And then again, from a performance standpoint, when you are dealing with a CP map, back up concurrency primitives, right? It's one field. So if I have an atomic reference, I'm working with that single piece of data. And I can have multiple applications, but they may all, or multiple clients, but they're all writing to that single piece of data. When you're talking about a CP map, you're talking about a distributed data structure. So you're talking about potentially having reads and writes happening to different partitions of that map. How is that going to affect the performance? Every time you write to a consistency data structure, you have to run raft. So if you have 100 clients that are all writing to the CP map, every time a write happens, we have to run raft. If they're all trying to write, 100 clients trying to write at the same instance, we're going to have to run raft 100 times. Now, so you need to, you need to make sure that you're understanding the performance implications of this. We do have some performance testing that we did. There's a blog forthcoming that will show comparison CP to AP under different conditions. So I will leave that for the performance experts. Just right now, I just want you to understand that there is some overhead that's incurred. If you are using multiple CP map structures, distribute those groups across as many individual cluster members as you can. So instead of having one, again, in this example here, I've got 7 members in my cluster. I don't want to have all of my CP maps running on the same 3 systems, because they're going to bog down those 3 systems and the other 4 aren't going to have nearly the same load. By doing this, by saying, okay, I'm going to have map 1 and group 1 and map 2 under group 2, I'm distributing that raft overhead. And again, hopefully that makes sense. Yeah. All right. So I want to quickly switch over to, this is a hands-on demo. This isn't just a demo. This is actually a tutorial that is available to you. If you go under our tutorials page in the documentation, the CP subsystem, I'm just going to show you some highlights from this demo. But we have an entire Docker setup with the CP subsystem running. So Docker compose up. I am bringing that up, and then I will switch over to the pretty application. There we go. All right. So what I've brought up for you is a cluster. Well, I'm showing it to you in Docker here. So I've got 3 Hazelcast cluster members, and I have Management Center running. So that's the other pretty thing that I can show is, let's take you into Management Center for this. I do not know why it is running so slowly. There we go. All right. So if you view our cluster, switch to CP subsystem. So we have a whole dashboard for CP subsystem. All our CP members are available. We don't have any groups set up because we don't have any data in the CP subsystem yet, right? So we're in a holding pattern. We're here, we're ready, we're waiting to form a group and just hold some data. So let's see. Okay, so what I've just done is I have opened up our command line client. So now I have a client connection talking to the CP subsystem. I've just got it pre-configured for the Docker setup that I've got running. And again, this is what I'm working with is that lab environment that you'll download from GitHub if you do this lab exercise. So I can now do CP map. Actually, I'm gonna cheat a little bit. Let me exit out of this. Okay, I have a CLC script. So where is my script? Okay, I can't type today. Okay, so this is a simple script for CLC, but what it's showing you is it's showing you here's the command that we would need to run data and add data into a CP map. So if I go back into, I can use that same command. I'll just do it by hand. So what I'm doing is saying, all right, create a CP map, call it Trek TOS. And in key 1, we're going to set it to helps if I type the right command. CP map, not CP. Okay. All right, so magic is happening in the background. And so we've just created a CP map. Now it takes, there we go. We have now in our system, we now have 2 groups that have been created. We have the metadata group. This is the group that maintains the data for the CP subsystem itself. And we now have our group called creatively default with 3 members. I can now go under CP maps. Okay. I see what happened. Excuse me for a moment. This is the updated system, and what I forgot to do was add my license key to Management Center. This is what happens when you do a live demo, right? So I have a license key that will go into under settings, license, boom. Now everybody's happy. Now let's try this again. CP maps. And there's my CP maps. Sorry about that. So I have a CP map. Yay. And now I'm going to go back in and I'm going to use my CLC client to forgive me. And I just added a bunch of fields to that. And again, there we go. So that's updated. So now we have 9 entries. Our map is split across our 3 clients. Everything is great. Now, what's going to happen if I lose one of these members? Well, let's pick a member and turn him off. Now I'm going to be kind of careful about this. In this environment, what I'm about to show you actually matters. Okay, so if we look at the metadata group, for example, the metadata is maintaining the information about the CP subsystem itself. If I lose the leader for this system or for the metadata, if the metadata can't recover, the entire CP subsystem crashes. So I want to be careful and make sure that I don't kill off the cluster to the extent that it can't recover itself. Again, in the real world, this is going to be less of a concern, but because of the way I'm doing things inside this Docker cluster, it's a little bit funky. I'm just going to kill off one of these group members. Let's go ahead and see what happens if we take out the leader. All right. So I'm going to go over to Docker. 18.0.5 is, okay, which one are you? Yeah, we know you're the leader. Okay, I'm looking at the startup. Go back to containers. Come on, I know what I'm looking for. I'm used to doing this from the command line. We'll just take, let's see. Who are you again? Stop that. Okay, so this system is 0.4. Let's just take out 0. Why are we doing this? Which one are you? You are, pardon me while I poke around here, guys. Okay, so this one is 0.5. So we're going to go ahead and just stop this system. And go back to it takes it, and again, remember it's going to take a few seconds for the heartbeats to fail. So we'll let it do its thing. Actually, what I can do is bring up the log on a system that's not stopped. Okay, we can already see that it's renegotiated. Remember the leader was 0.5. Okay, now we're renegotiating new leadership. Okay, so 0.4 is now the leader of the group. This will update itself eventually. There we go. Nope, it's still not quite there. I still haven't quite figured it out yet. So that's just Management Center. Again, let me go back and let's show you those logs and point out what I was talking about. Okay, so this is on the system that is still up and running. You can see that, you know, the new leader membership was negotiated. So if I go back up to the initial log, okay, so initial negotiation was that the leader of the group right here was 0.5. We took 0.5 out of the equation. Call it a network partition, call it we turned 0.5 off, whatever. So because that's the leader of the group leadership has to be renegotiated. So that's what we're looking at here, is that there's a conversation between the two remaining cluster members. 0.2 is elected leader. 0.4, this particular system, is still a follower. That's fine. We still have majority. The cluster is down to 2 members, but notice that the CP group is still keeping track of this member 0.5. And I said that we're going to retain group membership in memory until we either manually remove it or it times out. And the default timeout for that is 4 hours. Right? So that we're treating this as, if we treat this as a network partition, we want to make sure that we can recover. And hopefully, if you're in a partition condition, the network is going to come back within 4 hours. And again, when that cluster member comes back under partition conditions, he should have his group membership data in memory. He'll come back, they'll update that returning group member. We're back to a full group complement. See if we've caught up over here yet. Okay, no, of course we have. Derp. I keep looking for this to drop. The member count is still 3, but you'll notice group 5, he's not staying up to date. He's dropped out of this. He's not an active group member. We're still retaining his group membership, but he's not communicating. We're under partition conditions. to go back and show you that the client is still running. Come on. Forgive me while I forget the syntax. You have to use the / because it defaults to wanting to use SQL searches. Right? Okay, I don't know what's going on here. I'm going to. Oh, okay, created a map when I did that last one. I don't know why I did that. All right, so my data is still accessible. The bottom line is that the data is still accessible in that map because I still have a majority that's running. What I wanted to show you was bringing this group member back, keeping in mind that that group member now, because I stopped him, right? It wasn't a network partition. He actually rebooted. So when that group member comes back, I don't have persistence configured. That group member has no data in memory about the CP subset, the group membership. So let it come back up. We'll watch. So the cluster came back up. I now have cluster members of 3. We've done some partition migration, which is exactly what we should be doing. But when I come back to the CP subsystem, you'll see that this member comes back and he doesn't have any data in memory. We didn't configure persistence. When he rebooted, it knew about the CP subsystem, but this group member didn't retain any information about its group membership. The other members of the group still think that he's in the group, but because he didn't have that group membership in memory, he can't return. He can't rejoin that group. So the only thing that I can do to bring this group up to full membership now is to remove that member and then promote that member back into the CP subsystem. Now, if I go back, look at the stats, he's back up and running. He has rejoined the group. This still needs to update because he will not rejoin as the leader. If I go back over to Docker, you will see that he's rejoined as a follower, and the leadership has stuck with the leader that was elected when he disappeared. I hope this isn't. I haven't gone too far down a rat hole here for you guys, and I'm looking at the time as well, Mel. I'm on it. What I suggest that you do is go ahead and take the 10 minutes that will take you to do that tutorial that I mentioned. I think Mel's said she was going to put the links in the chat, which are there. But yeah, do the tutorial because I have you walk through the difference between setting up a system with 3 members and setting up a system with 4 members, and really try and drive home, how those failover works. The CP map itself is easy to use. It's the same key value data structure that you've always had. So that's easy. It's understanding how we're doing that. We're providing that consistency that's gets a little bit confusing in terms of setting things up. So having said that,
Alrighty, let's see some questions. So one question that came through, what is the performance difference between using CP map and IMAP?
right, and that's a good question, and it's any type of performance questions. It's going to be it depends, right? How big is your cluster? What is the CPU power? What is your network configuration, et cetera, et cetera, et cetera. uh, Randy May, one of our principal architects, has done pretty thorough performance testing, comparing CP and AP under the same conditions, so he can give you some base numbers. He's working on a blog on that right now. So stay tuned and look for that blog entry. I mean, the best that I can tell you is that it's obviously slower for writes. It has to be because of Raft. How much slower? That depends on a whole lot of other factors that, yeah, the specifics. It's easier to just say, okay, here's apples and apples comparison between AP and CP given this configuration.
Got it. Well, look out for that blog coming up soon. And one more. What can I use Java concurrency primitives like atomic long and atomic reference instead of CP map?
So you can use atomic reference for or atomic long for storing one piece of data. Why would I want to use a CP map versus those individual structures? And the answer is because they are singular data structures, right? They're not a data set. They're a single entry. So if you are maintaining, like if you're a financial institution and you are using an IMAP to track transactions, right? You want to have more than just one piece of data in that field. You want to have, here's the customer, here's the transaction number, here's the, several different fields. You would have to use an atomic reference, a separate atomic reference for each one of those fields, and then have to track in each one of those and somehow in your code align those so that they're all together. Using the CP map gives you that simple key value structure that says, all right, key one, and then here's all the fields that go with that key one. Key two, here's all those fields that go with key two. Especially if you are going to then, offload that data to some, back-end data store for permanent records. Having the CP map, having that key value store, it's easier to program. It's easier to work with than trying to do it with all these individual pieces of data, right? You've got a data set now. And so you have all the convenience of, an actual database style structure as opposed to individual fields of data.
So thanks, Handy. And well, that is all the time we have for today. If you have any other questions for Hendy or the team, we are also available on Slack. Feel free to join that. And just to wrap up, we will have next month's Hazelcast office hours. We'll be talking a little bit more about Hazelcast Flow. So feel free to register for that one when it's live. And well, that's all we have. So thanks for joining today, guys.